Thank you all so much for being here. It is Tuesday, June 10th at 2:15 p.m. here in Anchorage, Alaska at the 246th meeting of the American Astronomical Society. I am Kerry Hensley, the Deputy Press Officer for the AAS, and I'm assisted today by Lexi Galt, our AAS Media Fellow, as well as Susanna Kohler, the AAS Press Officer, who is assisting remotely. We also have Astrobytes Media Intern, Lucas Brown, who will be assisting during the Q&A. I just want to remind you that the materials from this morning's press conference on planets, exoplanets, and brown dwarfs have all been uploaded to the press kit, so you can find the slides, the press releases, and the briefing video there. We will also have press releases associated with this afternoon's press conference. You can find those in the press kit as well as in the press conferences Slack channel for this meeting. So a brief overview of the ground rules in case this is your first ever AAS press conference, in which case, welcome. This briefing is being recorded and live streamed to YouTube. It will also be archived on YouTube after this press conference is over. I'm going to give a brief introduction to the topic and introduce our presenters. We'll then hear from them in the order in which they're sitting. We won't take any breaks for Q&A after the individual speakers, and then we'll have Q&A for all of our presenters after we've heard all of their presentations. So for those of you watching in the room, please remember during that Q&A session to include your name and your affiliation, as well as who your question is for. And that goes for our folks watching on Zoom as well. You can queue up your questions using the Q&A feature, and remember to include your name, affiliation, and who your question is for. One last note, if you could take a moment, please, to silence your phone or anything else that might make noise during the briefing. This afternoon, we're going to be hearing about new views and insights into the sun and its surroundings. So learning a little bit about our home star. First, we're going to hear from Craig DeForest of the Southwest Research Institute, speaking about the polarimeter to unify the corona and the heliosphere, or PUNCH, giving us a mission overview and telling us about first light. Next, Nicholeen Viall of the NASA Goddard Space Flight Center will tell us about the Coronal Diagnostic Experiment, or CODEX, and its first light. So lots of new observations being presented here this afternoon. Then third, we'll hear from Juie Shetye from New Mexico State University and Armagh Observatory and Planetarium, and Mausumi Dikpati of the High Altitude Observatory, NSF-NCAR, talking about cracking the solar code, hybrid machine learning for predicting hemispheric bursts and cycle trends. Finally, John Linker of Predictive Science, Inc. will tell us about a near real-time data-assimilative model of the solar corona. And with that, I'm going to hand things over to our first presenter.
Thank you very much, Kerry. Let's see, we can pull up the slides here. Looks like that's on. Good. Okay, so I'm going to be talking about first light for the PUNCH mission. I'll give you an overview slide, but the tagline here is space weather like you've never seen it before. And I promise you, you have never seen anything quite like this. So I'm here talking about PUNCH, the polarimeter to unify the corona and heliosphere. Our mission is to identify and understand the corona and the solar wind that fills the solar system as parts of a single unified system. And so we want to track space weather from the sun to the earth in 3 dimensions. And we want to measure the solar wind globally around the entire star in near real time. Our data that we're using is polarized white light images, very wide field. So these are very similar to what you might collect with, say, a cell phone camera, right? Visible light images, things that are in principle visible on the sky, although they're very faint. Our mission design, we have 4 small sats. They're acting as one single instrument distributed across those 4 spacecraft. They're in sun-synchronous polar orbits, so they're in sunlight all the time, flying over the dawn-dusk line. And why do we have 4? Well, we had to spread them out around the planet because we need to look out in all directions at once, and the planet gets in the way from the point of view of any one spacecraft. So we had to spread them around the planet to look everywhere all at once. We launched in March our spacecraft are drifting into the correct geometry for science observations, and they'll arrive there in mid-July, but they're close enough now that we can produce preliminary results. So we're still finishing commissioning in the sense that we have commissioned the instruments, but the constellation itself is still forming. And calibration on the ground is still in progress. So these data really are quite preliminary, but they're good enough to show you what we can do. So this is what we can do. This is an image of the 90 degrees of sky centered on the sun. And we've background subtracted it in a rudimentary way. We will do much better once calibration is complete. But for now, you can see many familiar constellations. You can see the moon on the left-hand side of the image over here. And you can see the sun in the middle, that tiny speck. And so I'm going to run the movie here. As we orbit the Earth, the fields of view move around, and you can see coronal mass ejections, one coming straight at us and one heading off to the north. Now, to emphasize just how new these data are, the second CME happened less than a week ago, and we're presenting it to you today. So you can see the Milky Way and so forth in the background, and various other planets moving through the field as these CMEs evolve. Now, that halo CME is something you have never seen before. I'd like to call your attention to the white circle near the center of the field of view here. That circle represents the LASCO field of view. That is the largest coronagraph currently used to forecast space weather. Now, you've seen halo CME movies before if you've paid attention to the science press, but you have never seen one 30, 40 degrees from the sun, which you are seeing right now. So you're seeing something that is literally washing across the entire sky of the inner solar system as it comes toward the Earth. In fact, we were able to track that halo CME at 4 million miles an hour until just a little under 2 hours before it impacted the Earth. We might be able to do even better once we're calibrated. So we are tracking space weather from the sun to the Earth, even with our preliminary data sets. So the 31 May is the halo CME that you're seeing in this movie that caused the aurora just a couple of weeks ago, less than a couple of weeks ago. And the second CME, the one that's going off to the north, is the one from last Tuesday that's heading northbound at about 1.5 million miles per hour. So the yellow dot is the sun, the white circle is the field of view. We are taking data continuously right now. As we hold this conference, the constellation is in operation. We're taking a fresh set of images in full polarized light, so a polarized image sequence every 8 minutes. We'll do that moving to once every 4 minutes next week and carry on for the entire mission. These are preliminary data. They look good now, but they are going to look fabulous once we're done with calibration later this summer. This is a still just sort of showing one frame from that movie, showing what the CME looks like about halfway between the sun and the Earth. And I've outlined the leading edge of that coronal mass ejection in purple, just with the dots to guide your eye. But we can see that right up until it reaches the edge of this very wide field of view. This is first light from one of our instruments or one of our cameras, the narrow field imager. And this shows just a single still from that northbound CME, again, last week. And I want to call your attention to the tremendous amount of detail we can see in that CME. Now, coronagraphs in general require a great deal of calibration and background subtraction processing to remove various sources of stray light and backgrounds in order to reveal the fine structure of the corona. So the fact that we can show you this now is remarkable. The other three cameras are wide field imagers. These have a field of view that's roughly 40 degrees across, a little bit over. And so they see a large portion of the night sky. This is the very first frame from one of our wide field cameras back in late April or mid-April, just showing various constellations and faint features, including the asteroid Iris, which we saw in the very first exposure. That's a 9th magnitude object. So if you're here at the AAS, you know what magnitudes are. That's pretty faint. So we have 3 of these looking in different directions to make that mosaic you just saw. Our small sats are small. They are about 1 meter long, so a little over 1 yard long. And here they are back in February at Vandenberg Space Force Base, being prepared to be mounted on a Falcon 9 rocket and launched. You can see they're just sitting on tabletops. 2 people can lift one up. This is the satellites integrated with the SphereX mission, which we co-launched with, and ready to be bolted onto Falcon 9. Over here, the punch is all mounted to this adapter ring, and that's SphereX up above us. These are the launch videos just showing telemetry from the launch vehicle as our spacecraft spring deployed. They've been going at about 1 meter per second ever since March 12th, and they're drifting into the correct relative spacing now. So, in summary, we are revealing space weather as you've never seen it before. This is something that very few people have ever seen before today, and before last week, nobody had. The 4 spacecraft constellation is still completing commissioning. We're just drifting into the right geometry. We have tracked a CME continuously from the sun to the Earth. This is the first of many, I'm sure, and the best is still to come. Thank you. I'll hand off to Dr. Nikki Viall, who will talk about what's going on in the middle.
All right. Okay. I'm talking about CODEX science. I'm the CODEX science lead. Jeff Newmark is the PI, and Marta Casti, who's in the audience, is the calibration lead. And I'm going to discuss the first light results that we took with CODEX. All right, so to begin with, actually, I'm going to back up and show you a total solar eclipse. Hopefully, you guys had a chance to see the total solar eclipse that came across the United States last year, or this one from 2017 that came across the United States. Of course, what happens in a total solar eclipse is the moon comes between the sun and the Earth and blocks out the main body of the sun and reveals the corona, the atmosphere of the sun around it. That's how we get these beautiful punch images, and that's also what CODEX does. CODEX is a coronagraph, which makes artificial eclipses because these eclipses happen rarely and not long enough, and that is one of the reasons that we fly these instruments to look at the corona all the time. So CODEX launched on November 4th, 2024, and it is installed on the International Space Station. And that's what these pictures are of, CODEX being installed on the International Space Station. And it has been taking data of the solar corona and the solar wind since December 20th. Here's another view of CODEX on the International Space Station here. CODEX is a next generation solar coronagraph. The traditional coronagraphs, like what we saw in PUNCH and previous coronagraphs, measure density, electron density. CODEX is special because it also measures temperature and velocity, which means that we can really get the energetics in the solar corona and in the solar wind. NASA Goddard Space Flight Center leads the scientific and technical breakthroughs that enabled CODEX, supplemented with expertise from Naval Research Laboratory and Korea Astronomy and Space Science Institute, and support from Italy's National Institute for Astrophysics. So by combining all of these measurements, we get a new understanding of the physics of how the sun makes the corona, how the corona makes the solar wind. And what's really important is the ground state of space weather. CODEX is really focusing on the daily variations that happen in the corona and the solar wind, in contrast to the large solar storms that Craig showed. Measurements of the density structures, like we've had with coronagraphs and with models like I'm showing here, predict and show us that there's a tremendous amount of structure in the corona and in the solar wind on a regular basis, even without a big solar storm. So what I'm showing here is a model of a thermodynamics taking place in the corona. And here we've zoomed in on a particular type of structure in the corona called the coronal streamer. You can see the magnetic field holding the plasma. Hold I'm going to play that again. And what you're seeing in the color bar is the temperature. Red is hot. It's twice as hot as the cyan color there. So you can see the tremendous amount of variability in and structure in the corona. There are no coronal mass ejections and no solar storms that are taking place. This is a quiet day on the sun predicted by this model. And CODEX is going to does have the ability to see these kinds of temperature variabilities. All right, here is a CODEX image. So CODEX measures the solar corona and the solar wind by making an artificial eclipse. We do that by having an occulter that's tennis ball size held in place by 3 baffles. And here I'm showing one of these coronal streamers like we saw predicted in that model. This, though, we're just looking at density like a traditional coronagraph. This is a temperature map of a coronal streamer. So we've zoomed in on one of those structures, and you can see over the course of a couple of hours, the temperature changing and evolving just exactly in the way that those models and previous measurements suggested we might be able to see with CODEX. So the red is hot and the blue is cold. And we're especially excited to put CODEX in the context of our other heliophysics assets. Here I'm showing that CODEX streamer pasted on top of, put adjacent with LASCO SOHO images. The inner yellow dot is the ultraviolet image of the corona shown close to the sun. CODEX is there up on the top, and then the LASCO coronagraphs are shown in the outer field of view there. So we have the details of the energetics in that streamer, and we can put it in the context now of this global structure by combining all of these different fields of view. And by doing this, we can really constrain the next generation of coronal models and solar wind models so that we can understand everything from the ground state of space weather all the way through the big space weather events. So Craig talked about the enormous field of view that PUNCH provides. Here's a total solar eclipse from 2017. The PUNCH field of view goes from that total solar eclipse all the way down to the horizon, all the way up to the zenith. And CODEX fills in the middle there, fills in the energetics that provides those structures that fill this space. So in conclusion, CODEX is already providing a new understanding of the dynamic and variable way that the sun makes the corona and the solar wind. It's quantifying the energetics as these processes occur, and is really going to put tremendous constraints on the modeling of the future generation of the corona and the solar wind and the ground state of space weather. Thank you.
Okay, Juie, Shetye, and I, Mausumi Dikpati, will be presenting Cracking the Solar Code, Hybrid Machine Learning for Predicting Hemispheric Bursts and Cycle Trends. You can see that the solar cycle, you all know solar cycle has, solar activity has profound influence on the terrestrial environment in the form of hazardous space weather. However, the solar cycle does not progress very nice, smooth sinusoidally. By contrast, they progress in the form of short-term bursts, like enhanced burst and followed by a relatively quiet period. This burst, these bursts, basically the major CME and flare events occur during these burst decisions. So it is important to predict these burst decisions. When is the next burst coming? Actually, these are not random. These bursts have a quasi-periodicity. And physical origin of this quasi-periodicity is the interaction of global magnetic fields with global solar Rossby waves. However, the question is, when is the next burst? We are in June now. July, August, September? Will both hemisphere, north and south, have bursts together, or will it occur one after another? So that's what you are going to hear from Juie from her model.
Thank you. Thanks, Mausumi. Right. So yeah, that's true. We don't know when the next big flare is happening. And so that has been our motivation, trying to predict some pattern-like things in the sun. Okay. So you'll also notice from this plot that both the hemispheres kind of don't follow each other. So patterns in the north and the patterns in the south are quite different. And that's been the motivation for this study. Okay? So the results that we have, okay, the big question, when is the next massive solar storm going to happen? Where is the possibility? Or when we are going to have the next space weather event, when I'm talking about this? So we know we are in kind of the maxima, but we had few months of quite a period. And so we can, our model, our approach is able to predict that right now we are in a maximum phase and it's going down and it's expecting the next burst in the north to occur somewhere around November this year. And the same logic goes in the Southern Hemisphere. The next burst is occurring around December. So with this logic and the results, we also see that the model tries to predict not only the size, like when it's going to happen, but how long is that activity going to happen. So we see that it's going to be around starting somewhere June, July, and it's going to continue in the north. And then you are going to get some phases, some time where there are 20 less sunspots in the north. Okay? And then the peak activity occurs again. The same thing goes in the south, but the model, it predicts like a little bit of asymmetry in there. Like, so the first burst is not completely quietening down, and it's predicting that there's going to be like a next burst, like a mini burst happening around somewhere around August. And then it's predicting that around December, we are going to see the rise. Okay? So these are kind of predictions that we see right now. When you combine the total effect of these cycles, we can predict on the sun where next peak of the activity is going to happen. So we add these things up. And the next question that we have is, so now we know when there's going to be the next storm. So what do we do about it? So that's something that we're investigating. Okay. So why predict this? First of all, last space weather events cost $2.4 trillion. And so we want to find a way to identify next big space weather event. And then instead of like relying on an 11-year model, we're trying to see the intricacies between the sunspot numbers that we have, coming down to a period of 6 to 18 months. And that's what we are honing down and trying to give you, or give the community kind of a way to know when the next thing is happening, which will last for 6 to 18 months. Okay? So how I did it, a bunch of magic boxes. So my first kind of helper or a magic box that I had was a mathematical model, which is a Gaussian curve. So you can see the bursts kind of have a peak, have a maxima and a decline. So we kind of fit a Gaussian model to it, a numerical model. The second helper that I have, the second magic box that I have is Sarima, which is a statistical programming model that I can use to forecast. So it's used for forecasting hedge funds and share markets ups and downs. Okay, so it's used for kind of non-stationary prediction model. And the third one is machine learning. So whatever burst properties I have, Sarima is to, it looks into patterns, and we don't see those patterns in bursts when we look at them collectively. So I use a machine learning approach where I use something known as random forest. And so what we did was we took 50,000 plus sunspots, we put them in these magic boxes, and then we predicted the outcomes that I just showed you. And And so I will finish my slide with like why we care. We really care about these things because I really want to know when the next big flare is going to happen. And so for this prediction, we are trying to predict that, okay, in November period is going to be the next maximum activity kind of period. And in that period, of course, we are expecting geomagnetic storms, we're expecting solar flares, and we're also doing it in a way, predicting this as a short, in a short scale, short duration for the first time. So we know we have people predicting how a flare is created, and we have those long-term predictions. We don't have anything in middle, and that's what we're trying to bridge the gap. And thank you.
Find a mouse. Oh, there it is. Okay. I'm John Linker from Predictive Science. I'm going to be telling you about our new real-time data assimilative model of the solar corona. Earlier in the briefing, we saw these beautiful observations of the solar corona and solar wind. And the corona and solar wind are, particularly the corona, is a very hot plasma, and it's permeated by the solar magnetic field. And it's understanding the solar magnetic field is the key to understanding the physics of the corona and solar wind. And we measure the magnetic field, or it's easiest to measure it in the photosphere. That's the sun's optical surface. So to understand the corona and solar wind, we have to extrapolate that field outward. We do that with a magnetohydrodynamic, or MHD model called MASS. And that model also gives us synthetic observables that we can compare with observations. The movie that you're watching right now is a visualization of the magnetic field from that model. This is, you're seeing it updated hourly, and this was over 32 days that we did for the prediction of the corona prior to the 2024 April 8th solar eclipse. And so let me go to the next slide. Here we go. So as I said, it's actually a tradition of our group that we predicted the structure of the corona prior to eclipses. We knew going into 2024, though, with this time of near solar maximum, that the sun is very dynamic. And we decided we really needed a new approach to this. And so we developed this time evolving model that continuously assimilates data and is updated. And we posted the results hourly to our website. The previous movie you were watching was that hourly prediction. One of the things that came out of this, though, was that the resulting structure is highly dynamic, and the simulated corona is more like the real corona in that way. And so we think this is a new paradigm for coronal modeling. So the data that we need to assimilate are photospheric magnetograms, and primarily from HMI, which is aboard the Solar Dynamics Observatory. And the leftmost movie you're watching there is that field projected onto a latitude and longitude plane. That in turn then is fed into our new surface flux transport model called FT, because we primarily have observations of the magnetic field along the sun-Earth line. We need an entire global coverage of this field. So we use this model predicts how the field evolves in the regions that we're not observing and gives us a full sun map. And so you can see there, the boundary condition is the radial magnetic field. You can see on the right top image. And then on the bottom is you're actually seeing the magnetic field in the model evolving. And a key component of this is the observations we're ingesting don't tell us about how energized this field is. So we developed a heuristic method to energize this field in a way we think is like how the corona is energized. And so that's why you see lots of activity going on here, and that turns out to be a crucial new aspect of this model. So as I said, this model evolved in time. What you're looking on the left are EUV observations, extreme ultraviolet from the Solar Dynamics Observatory. And on the right are our simulated observable for that same line, 193 angstroms. And I should say, because our energization that we are hoping is going to be statistically like the sun, but it doesn't match it's not matching the true fields there because we don't have that data. So so in some sense, what you can see here is that we're getting, just like the real sun, we're getting lots of small scale eruptions, small scale flares. There's formation of filament channels. And it's actually remarkable how much it actually looks like the real sun. And now what I'm showing you are, on the left is the coronagraph, the Core 2 coronagraph on stereo A. And on the right is our simulation of what that coronagraph would observe. And again, in truth, the real sun was more energized. There was, in fact, a major X-class flare during this time period. And so it has more eruptions than our model does, but nevertheless, our model has lots of activity erupting all the time. And indeed, if you watch movies of observations of the sun, this is how the sun behaves, especially near solar maximum. So all of this was to predict the structure prior to this eclipse. And on the left, you can see the prediction as it stood approximately 10 hours before the actual eclipse. And in the middle is a processed eclipse image that we have obtained from the group in China. And we've attempted to process our image in a similar manner. What you can see, though, is that the structure, particularly on the east limb of the sun, that's for non-astronomers, that's the left side. And there's a streamer there that's not really in the model. And when we look at the magnetic field for the sun, which is these bottom images, that's the solar magnetic field stretched out in latitude and longitude. And the red and blue regions, the darker red and blue regions are what we call active regions, where we have strong magnetic fields. You can see where that line is. That's what the model thought was the magnetic field on the east limb at the time of the eclipse. When we wait 7 days and see what rotated into view, we see there was a lot of new active regions that appeared that they weren't in the model because we didn't have any observations for them. And in fact, this, of course, is not perfect because this isn't the data that was really there on April 8th, but nevertheless, because these active regions then diffused and changed their structure to some degree. But we had continued to run our model. And so then on the rightmost image at the top, you're seeing what the predicted corona looks like when we include this new data. And you can see how this streamer has changed a lot in its position. And this just demonstrates that indeed it's the magnetic field that determines the structure of the corona. And that's those are the observations that you need to really understand things. Just wanted to say that, as I already said, very excited about the new observations that are coming out. We're anxious to do modeling that can help understand those. This is what our simulation would predict that Punch would have seen during this time period if it was flying. Of course, we don't have the star fields and all of that in yet. So as I said, and the CODEX observations as well, very excited to work with that data and use it to constrain our models. So as I said, we demonstrated a continuously running model in real time of the corona for the 32 days up to and after the April 8th total solar eclipse. The model exhibits this highly complex coronal structure that we actually see during this time period. And I'd say this approach is more akin to how terrestrial weather models are run. And so we think that this is kind of the future approach for space weather forecasting models. Thank you.
All right, we will shortly get our Q&A session underway. So again, for those of you here in the room, please be sure to state your name, your affiliation, and who your question is for. And for those of you online, feel free to use that Q&A box to queue up your questions. All right, let's start with questions here in the room. Ethan.
Hi, this is Ethan Siegel from Starts with a Bang on Big Think, and my first question is for Craig. Craig, I'm really excited about the videos you showed of Punch. They're the first ones I've seen, and you're right. I've never seen anything go from, such a wide field of view to track a CME like that. You talked about opportunities for understanding how things get transported from the corona to Earth. I'm really curious about what type of opportunities there are for synergy between an observatory like DKIST and Punch to sort of unify the understanding of how things like energy is transported from the photosphere to the corona and out to the Earth and beyond. Do you have any insights to share into that?
I do. It turns out we need all of these fields of view, and they're connected in ways that are not obvious to the naked eye, but that are deep in the corona. We see structures in the outer solar corona with existing prior instruments, and we will see them with Punch, that correspond to structures that are smaller than a granule on the surface. And so these structures that are being revealed by the ultra high resolution images from DKIST may very well actually be the same things that we see moving through the outer corona. So understanding this complete system from stem to stern, as it were, is important for trying to understand how stars work and how our home works. I mean, we live here.
This is Bruce Remington from Lawrence Livermore National Lab. This is to anyone but primarily Craig, just because that's where I jotted down my question. Is the energy source behind these coronal mass ejections due to magnetic reconnection?
I'll say the magnetic field is the only reservoir of energy that's sufficient to drive a CME. However, magnetic reconnection isn't necessary. It is probably intrinsic to many of the CMEs we see, but the energy is stored and released from stored in and released from the magnetic field. There are many mechanisms that could release that energy. Loss of equilibrium is one. We've seen eruptions where, for example, mass is tamping down a dip in the magnetic field, and if that mass slides to the side, everything goes unstable. So there are multiple instabilities that can cause CMEs. However, the very strongest CMEs are associated with magnetic reconnection.
Great, thank you.
Other questions here in the room? Ethan.
Thank you. This is a question for Juie and Mausumi. I hope I said those correctly. I wanted to ask, I'm a little concerned about what you're attempting to do here because this is such a chaotic system. So even if you know all of the initial conditions and the rules governing your system, which it's arguable you don't, but even if you did, your predictions, it's going to be difficult to make specific ones about when a flare or an ejection is going to occur. Even if we can say something intelligent about the likelihood in a general sense of a risk of elevated activity, isn't this inevitably going to be like trying to predict an earthquake, or for an astronomy analogy, trying to predict the eruption of T Corona Borealis, where the uncertainties on any prediction are going to be far greater than the precision of any prediction itself?
So something that, it's not as easy as putting garbage in and garbage out kind of a situation. But I think when we are trying to make the predictions like the ones that I showed you just now, we're trying to make it more and more having physical information. Like when I'm feeding something into the statistical model, I'm actually feeding the properties that are happening in the bursts. So going back to like what Mausumi was talking about the physics behind these things. So Rossby waves analysis or some other theoretical models do predict 6 to 18 months periodicities during the solar cycles. So those happen. What we don't know from simulations is when they happen. So we are trying to get that information. And I showed you just the kind of the sunspot numbers, which is easy data set for us to kind of take down from internet in a way. So the next thing that we are trying to do is put in more parameters, like more cyclical parameters, more dynamo information to make the predictions more stronger. That's the next thing. So it's not going to be as easy as predicting anything. It's and then another thing that I did not talk about was to make the models more aware of some of the non-seasonal fluctuations that you see. So it's a mathematical model that thinks that everything is a sine wave or a cos wave. But in terms of like predicting something that is not statistical, like so not seasonal, it's a challenge. So that's where different machine learning models come into the play. So that's the future of what we think we should do.
My name is Meng Jin from Lockheed Martin Solar and the Physics Lab. So my question is for John. So John, very impressive modeling work. And my question is, so you mentioned that the eruption generated in the simulations is a small scale and less energetic. Is this because the coerced grid and the input magnetic map used? And also, would using the vector magnetic map help to generate larger eruptions?
Well, indeed, I mean, the first issue that we have is the data we're ingesting is only the radial magnetic field. Even if we had the vector field, though, the problem is we're seeing active regions when they rotate into view. So, and not just active regions, but filament channels and things. So that energy has been building up a long time out of our view and now comes in. So in some sense, without full sun observations, we're going to have to try to estimate that energy. And in some sense, I think, when you have especially a very large eruption, what you see is that active region comes up with a huge amount of energy. I mean, we can, in some sense, model that separately. I guess I'll advertise that we have a tool at the NASA CCMC, Community Coordinated Modeling Center, called Core-Hull CME. It allows you to take one of these backgrounds, and then you can experiment with flux rope CMEs, and basically anyone in the world can use that site. And of course, we're not the only group who models CMEs in that way. I think that is, I guess I would say, I don't think we quite have the data available to predict really large eruptions before they happen from this approach. But once you've seen a CME, you can then initiate such an eruption.
Hello, I'm Raphaël Attier, heliophysicist at George Mason University and NASA Goddard. So space weather operations in the space industry are more oriented toward nowcasting rather than forecasting space weather. So what key heliophysics knowledge gaps will Punch and CODEX address to ultimately improve space weather forecasting and enhance the space industry's resilience?
All right, well, I'll start with CODEX. So as I said, CODEX is really helping us understand the ground state of space weather. So in an Earth weather analogy, the big CMEs, the big flares, those are your hurricanes. If you're a space weather operator, you hunker down for those big events, and certainly they're very damaging and you go into safe mode. But you also need to know how to operate in the thunderstorms of space weather. So that's what we're calling the ground state of space weather. So when there's a thunderstorm, you still want to go about your daily activities. You don't hunker down, you don't go into safe mode, but you need to know that that thunderstorm is on the way. And so CODEX is going to help us understand that daily variability, those thunderstorms of space weather. And also, this solar wind is the medium through which all of these huge space weather events have to propagate through. So that's what CODEX is going to help us understand. It's going to help us understand the energization that makes all of these structures in the corona and fills the solar wind with all of the plasma. And I'll let Craig do punch.
All right, thanks for queuing that up. So both punch and CODEX track what you might call space weather thunderstorms, right? These mid-sized events. Punch will track all of these events from the sun all the way out. And so I like to compare Punch to a space weather satellite. If you're old enough, you remember a time before there were geosynchronous satellites monitoring hurricanes. And at that time, hurricane prediction was very difficult because you had to extrapolate from a very few ground stations. Once the satellites came on board, you could just watch. You could see the hurricane moving, and that made hurricane prediction much easier. So Punch is doing that now already for CMEs. Large CMEs coming toward the Earth can be tracked continuously from the sun to the Earth instead of extrapolated from the sun itself all the way out.
Bruce Remington from Livermore. This is for anyone. I'm sure it's a silly question, but you know, the sun is not the only star in the universe. So do we have any observational indications or theoretical predictions of that kind of phenomena, these dynamics of the sun from stars outside, you know, beyond the sun?
Yes.
Craig, start with you.
Yes, stellar variability is a thing, and we can observe other stars in the UV and see that they have coronae and that they vary. Other stars have star spots. However, the sun is the only star that's been proven to grow vegetables, so it's the one we care about the most.
Any questions in the audience? I have a couple, if you don't mind. A quick question for Craig. This is Kerry Hensley from the AAS. You mentioned that Punch is still in its commissioning phase. We've already seen some fantastic images, but we can expect something even better once it's out of that commissioning phase. Can you give us a quick sense of the timeline and when we might expect to see Punch enter the next phase of its mission?
So formally, we enter phase E next week, which is science operations. It will take some time before the ground system is ready to do the full background subtraction. We're required to release background subtracted data products by September, and we will have something in advance of that. But essentially everything that's not space weather in those images will be gone from those images when we're finished. So we remove 99.9% of the light that hits every camera frame.
Great. All right. Anything else here in the room? Anything online today? Okay. Well, with that, I think we can give you all a little bit of your time back. Thank you all so much for your attention and for your questions. Thank you to our speakers for sharing their science with us and to the PIOs who helped them prepare and prepared press releases. I really hope that you will join us here tomorrow morning at 10:15 for our final press conference of AAS 246. We will be hearing about recent and upcoming discoveries in the broader universe. And with that, I'd love for you to join me in giving our speakers one last round of applause.